Let's discuss the capacitance of a cylindrical capacitor, which you can see in this picture. Cylindrical capacitor is a system of two coaxial cylinders which are very long compared to the radii, and we consider it long because if it is very long compared to radii, we can consider a radial distribution of electric field, like in case of linearly charged uniform wire. Now in this situation, if we wish to find out its capacitance, then to calculate capacitance, we supply a charge Q from outer cylinder B to the inner cylindrical shell A. In that situation, on the inner cylindrical shell, a charge plus Q is spreaded uniformly as it is very long, and exactly equal charge minus Q will appear on the inner surface of the outer shell B. Now, if the charges are Q and minus Q, we can easily find out the linear charge density on the two shells, which is lambda and minus lambda, where the magnitude of linear charge density will be Q by L, because here we assume that the total charge is uniformly distributed throughout the length of the cylinder. Now, in this situation, the capacitance of the annular region between the two cylindrical shells can be given as, it will be charge supplied divided by the potential difference VA minus VB. And this is the capacitance between the annular region, because there won't exist any electric field outside this region, because all the electric lines which will originate from the inner cylindrical shell will terminate on the inner surface of the outer shell. So electric field will be in existence only in the annular region. Now, if we wish to find out this potential difference between the two shells, we know that from the axis at a distance x, electric field can be given as 2k lambda by x, that is that of a uniformly charged long wire. And if we know the electric field at a general distance between the two shells A and B, potential difference can be given as VA minus VB is equals to integration of E dot dx from shell A to B, that can be integrated from R1 to R2. And here we can omit this dot product because E and dx are in same direction, because we are finding the potential difference along the same line. So it will be integration of 2k lambda by x dx integrated from R1 to R2. And here VA minus VB we are getting is 2k lambda 1 by x dx integration will be ln of x within limits from R1 to R2. That will be 2k lambda ln R2 minus ln R1, that can be written as ln of R2 by R1. And if this potential difference we substitute here, the capacitance of the cylindrical capacitor will get is Q divided by 2k. Lambda we can write as Q by L ln of R2 by R1. Here Q gets cancelled out and the value of capacitance we are getting is, here we can also write this K as 1 by 4 pi epsilon naught. So it will be 2 pi epsilon naught L upon ln of R2 by R1. In some cases, we are required to find the capacitance per unit length of the cylindrical capacitor in case the capacitor is very long in length. So we can easily write down the capacitance per unit length of a cylindrical capacitor is, this can be written as C. This per unit length we are calculating, this can be written as this C by L. So this will be 2 pi epsilon naught upon ln of R2 by R1. That is the capacitance per unit length of the cylindrical capacitor. So just be careful and keep this result in your mind. That will be used in many cases.